Welcome back. In this lectures, we are going to start the next unit that is the pole placement techniques. So here we are going to design state regulator or state feedback controller as well as state feedback observers. So in previous lectures, we have already designed root locus method in discrete domain, its constitutional rules and examples, and effect of the sampling effects. So here the basic objective of the root locus. So basic objective of the pole placement technique is nothing but we are just obtaining the desired response using the poles locations. So using pole placement, we have to poles. We select the poles as per our desired characteristics on Z plane. So here we have to first design the state regulator, then we have to solve examples, and then after that we can go for the design of the predictive state observers. First we have to discuss the digital state space system, which is already covered in the previous lectures. So digital control system with the state feedback, a discretized model of the plant can be given as the written in this form. So where this one x k plus 1 equal to f x k plus g u k. This is the state equation, and output equation is the y of k is equal to c x of k, where the x is the state vector having the order n cross 1. Here the one input and one input we are considering a, and u is the scalar input and y is the scalar output. F is the system matrix that having the order n cross n, and g is the input matrix and order is the n by 1, and c is called a output matrix having the order 1 by 1. That is the CISO system base. And k is the integer value, is varying from 0, 1, 2, dot dot infinite value. So here before proceeding to design, we have to consider the following steps. First we are assuming, before proceeding the digital controller design, means we have to first design the state regulator, so our state feedback controller. So here assuming that all elements of the state vectors is available for the feedback, means all state variables are available, or we can able to measure these state variable using the conventional devices, and we can apply as a feedback to the controller. So design a state observer which estimate the entire state vector when provided with a measurement of the system given by output equations. And if these state variables are not available, then we have to go for the observer options. So we have to design a state observer based on the output information as well as input information of the system. We can able to estimate the states or unmeasurable states of any plant or any system. So finally we combine the control law and observer. So these two combination we can call as a state regulator. So they are just estimating all the states of the plants. Then after that estimated states apply to the controller, and controller they are controlling the plants according to the desired way. So now here you can see this is the state regulator. So first we are going to describe the state regulator. So in this case the control law for the state feedback controller. So you remember that in state regulator there is a state observer as well as a state controller. So suppose there is a plant, suppose this is the plant, and we have given the P, and this is the output is applied to the observer. So this is the observer I have given, and here this is the input. So this input is also applied to the observer, and observer estimating the states. Suppose this is the X cap, and here we are getting the Y. So this input we have to apply to the controller or control law. So this one, and it gives the u. So u will be given here. So this is the u. So like that we have to design. So here we are going to design this term. So here the nth order system we are considering. So u of k control law in discrete domain is equal to minus k x of k. This one is k is the capital K. So there is a typo errors. So this k is the state feedback gain. Having the order is also k starting from k1, k2, k3 kn, means it's order n by 1 by n. So resulting when we are putting u of k is equal to minus kx in the previous equation, that is the xk plus 1 equal to f xk plus guk. In place of uk you have to put generally this minus k x of k. So we are getting a x plus k equal to f minus gk x of k. So this is a resultant closed loop system. So dynamics of this system is nothing but as per desired response. So here the eigenvalues of f minus gk, this is the system matrix of the desired system. So are placed inside the unit circle in complex plane. The state xk will decay to the equilibrium state x0 irrespective value of x0. Initial perturbation in the state necessary. So in this case, we can able or we have to freedom to choose this state vector or this system matrix eigenvalues arbitrary, and we can place inside the unit circles. It may be real, it may be complex. Based on our desire, we can put. So necessary and sufficient condition for the arbitrary placement of the closed loop eigenvalue is that the system in equation A is completely controllable. Equation A means this is the equation first in previous given, that is the A equation I have written. So that is nothing but x k plus 1 plus this one equal to f xk, and this is the xk, then plus g of u of k. So this state equation should be controllable. If there is a controllable, then we can easily design or we can easily place these eigenvalues. If it is not a controllable, then we can convert into the controllable form. So characteristic equation of this is resultant equation. So we can write in this form. So zi minus f minus gk, and total matrix is taken as a determinant and equate to the 0. So here we have to find this value of k. This is the objective. Uh, this system matrix F, which is already known, and G is also known. Only we have to find K. So we can represent the characteristic equations in terms of the K. So then after that you can see here we have represented the characteristic equation in terms of the K. Now we come to the choose the desired poles locations. So desired poles locations, suppose desired poles locations are lambda 1, lambda 2, lambda dot dot lambda n, because nth order system is there, so n poles are there in the system. So we can choose and find out the correct equation. So here this fifth equation and fourth in previous equations coefficients we have to match and to find a k value. So this is the way, in this way we can compare equation 4th and 5 in terms of the coefficient to calculate the value of k. So this k is have different number of means k1, k2 dot dot kn. So each values we can compare with respect to a1, a2 dot dot an. So algebra for finding the gains becomes simple when state variable equations are in controllable and canonical form. So which is already discussed in state variable equations are in controllable and canonical forms. So in canonical forms, in observable forms, when we are designing the state feedback controller, then we have to represent all the system in controllable canonical form. If we are going to design the state observer, then we have to convert the system into observable canonical form. So in this way we can design, so we can able to easily find out the state feedback gains value. So here we have to consider two variables. So here first equation, this is the actual system correct equation we have given. This one actual state correct equation we have given. So using this controllable form. So this is the actual, and then we have to determine that these coefficients alpha 1, alpha 2, dot dot alpha 1, alpha n. So these value we already known and we have to list down. Then after that we have to design the P matrix. P matrix. So here is P, a capital P, another is the small p. A small p1 is small p1 is small p1. So this small p1 is nothing but equal to 0, 0. Oh, here we have to add the 0 or calculate the zeros based on the size of the F matrix. So this is the one, and U is the controllable matrix. So here controllable matrix we have to take the inverse. So this is the U is equal to G F G dot dot F to power n minus 1 into G. So this is nothing but a inverse of the controllable matrix. So you have to multiply with this matrix, then we are getting the P, and we can calculate the capital P. So this is the second step. Now come to the desired. So desired eigenvalues are poles we have to select it. Suppose this is the lambda 1, lambda 2, lambda n. So we have to product out and calculate the a1, a2, a3 dot dot an. Then we can directly calculate the gain k is equal to known a1, an minus alpha n, an minus 1 minus alpha n minus 1 dot dot a1 minus alpha 1 multiplied by p multiplied by this matrix. So we are getting the p. So alpha n is known, this is also known, an, these are all values are known, we can multiply, we can get. So we can directly write this formula. So this formula is known as the Acker formula. So here we can are using the Acker formula, so you can also design the k is equal to in this form. So here phi of f is the state transition matrix. So you know that any square matrix satisfy its own correct equation. So using the Clay-Hamilton theorem, so here they have calculated the phi f and u, so we can multiply, so we can get the k. So this is the A method based on the Ackermann formula. Second is the based on the this coefficient matching calculation, and third is we can simply correlate between desired and resultant matrix coefficients to obtain the k. So there are three steps, three methods to obtain the state feedback gain. So now come to the a suitable example. So here we are considering a state example in continuous domain. Here the time sampling time is given the 0.1 second. So this 1 second is the sampling time. So this is the A matrix and this one is the B matrix. We have to first convert this continuous system into discrete form. So this is the discrete form representation. Xk plus 1 is equal to fxk plus g uk. So here, as you already discussed, the f system matrix f in discrete domain we can calculate, that is equal to e to power at. So simply we can put, we are getting this form, and g is equal to 0 to t e to power a tau b into d tau. So we are multiplying, simplify and integrating with respect to 0 to t, we are getting this time. This is the G matrix. So now we can calculate the correct equation. So this is the actual system correct equation, that is we are getting the z minus 1 whole square. And you know that the controller u of k is equal to minus kx. So we want to calculate this k. This is the gain value. So here the second order, so there are two elements in the k, that is the row matrix k1 and k2. So we can put in this form. So overall resultant equations we are getting the f minus gk. So we can calculate the character equations. So character equation, this one we have to create here 0. So we are getting the character equation in terms of t and k1 and k2. This is the character equation. So here you can put the sampling time which is given in the question, 0.1 second. You can put and simplify this equation in terms of the k1 and k2. Then you come to the choose the desired value. We want to a system having the damping ratio 0.5 and natural frequency 3.6. So based on, we can design the discrete poles location, means a Z map in unit circle. So that is equal to e to power minus del omega and t into plus minus e to power j omega n t square root of 1 minus d. So we can put omega n, del and t value. So we can get z1 z2 this form. So we can obtain the character equation, means in form z minus z1 multiply and z minus z2. This is the z minus z2. So we are equating 0 and we are getting the character equation in this form. So here the coefficient, this equation coefficient, equation 1 and equation both are the equation same. So all the coefficients should be same, because this is also desired character equation, this is also desired equation. So we make and comparing, then we can calculate the k1 k2 value in this way. So this is the k is equal to, this is the 10 and 3.5. So this is the k state feedback. In this way we can calculate. But for the large order of the maximum third order we can easily calculate, but when the size is going to larger, so it becomes very complex to compare and obtain these equations. So now come to the state observer. So you know that if all the state, in previously we are assuming that all state variables are available for the measurements and we can easily apply. If all the state are not available for the measurement, then we go for the state observer to estimate this observer, and then estimated state we can apply to the control law. So here we have to first proceed to design a full state order observers. So what is the full order, what is the reduced order? So this state observer divided into two categories. One is the full state observer, second is the reduced order. Suppose a plant is there, so plant have certain suppose 10 number of the states are there. Out of 10, only 2 state variables we can able to measure, and 8 state variables are unmeasurable. So we cannot able to measure. So we have to estimate these state variables. So using the state observers. So we have two options. Either we can estimate all the 10 states using the system output information and input information. So this is the one case that is called a full state observer, and other is the reduced order. We only have to design we have to estimate only 8 state observer, that is the unknown or unmeasurable state. Only 8 state variables we have to measure using the reduced order observer. So we are not go for the other 2 state, we can directly feedback to apply with using the measurement devices. So here we are first going to discuss the full order observers. It's called a prediction observer. Why it is called prediction observer? You know that using the present value, we are estimating the next value of the states. That is the future value. So next future value. So that's why it is called prediction observer. So here you can see this is the general form: xk plus 1 is equal to f xk plus g uk plus m y of k minus c x cap. So here this is the state equation where f and g are the same as the previous we have considered. Y of k is the system plant output and cx of k is the observer output, and a small m is the that is the observer gain. So we can here. So you remember that in this PPT or in this reference book, they are taking the x cap, means estimated value. Normal x is equal to the plant state variables. So this is the size is same. When we are putting here and simplifying you control law, so we are simplify these equations. We are getting this form. So this is called error dynamics. So in this error dynamics we can obtain. So here x tilt is equal to actual state of the system minus x cap. So using this equation, we have to simplify this equation. We are getting in this form. This is the error dynamics. So the we can obtain the correct equation. This is the, so you can relate in state observer and state controller. So here you can see in state controller we are getting f minus bk. Here we are getting f minus mc. Means controller can be designed using the system matrix and input matrix. And observer we have to design using system matrix and output matrix C. So here we have to calculate this observer gain m. So then we have to calculate same process we have to apply. So here we have to calculate the correct equations of this desired value, and then after that we can choose the desired values poles location based on. Then we have to calculate that these desired values equations. So this equation and previous desired value equation both are the same, and compare and calculate the coefficient of the value. Means designing process of the K and M or both are the same. So here this in this way. So this is the diagram of the, so this is the plant they have given, this is the output, this is the actual output of the system. We are taking output, and this is dotted line is the represented by the observer. So here we have taken the input and this is the output. So this output is generated a error, and this error is applied to the M and added here, and this is the estimated state, and this estimated is spread back with this one. So we are getting the output, and this system can be so when we are transposing the observer these equations in between input matrix and C matrix, so that is nothing but it becomes controllable. So means controllable canonical form we can convert into the observable form. Observable form system each can be controllable form, which is already discussed in duality. So they're like a dual nature. So they have given a in another form. Suppose this is the system is given. So this system is dual form here. This one. So this system, this state equation plant dual form is given here. So for this one we can design. This is the controller and compare and control design this way. So this is the state observer. So here already this, so duality principle may be used to design the full order state observer by Ackermann's formula equation or by design procedure given above. So we can design Ackermann formula or using coefficient comparator. So duality observer and duality controller. So dual means if we are design a plant system state controller, so this state controller becomes as an observer for the dual system, and then observer becomes controller in dual system. So like that vice versa we can arrange this one. So we already discussed the pole placement technique, state regulator design and examples, and predictive state observer. Thank you.